So hope you practiced everything that we have discussed yesterday regarding the collections framework. Uh, I hope everyone is good with it, right? Hello, is my voice clear to everyone?
Yes, sir.
So have you gone through that split iterator that we have discussed yesterday and few other things that I asked you to demo today, right? So what are or one is split iterator and the other one is hash code are the two things that I asked you to do it, and the other one is uh, that capturing the driver state in Selenium. Anyone is ready with them?
Sir, I tried, but I'm not able to do that.
Which one? That it will take
Selenium
time.
one.
It's I'm asking about hash code and the split iterator.
Hash code I have tried, but split iterator, actually I saw, like, I didn't implement that.
Okay, that is fine. So any others gave the try? So again, I'm repeating this. That is very important. Collection framework is very important, and you need to know every inch out of it. So I recommend you to practice all the methods for one list, one set, and Q and DQ is up to you. Oh, it's not so frequently used when coming to our automation testing or STET rule. So maybe it's up to you. Like keep practicing them, and you'll get 50% of your questions from it. As I'm saying, I'm repeating every time. So let's move on to the implementations of the data structures. So we have seen different data structures like linked list, arrays, array list, stacks, vectors, and coming to set, tree set, hash table, queues, dequeues, and everything, right? So now let's try to implement like one from the list hierarchy and the another from the trees hierarchy and the other from set hierarchy, like hash table or something. So let's quickly move on to the linked list, and let's understand how basically the linked list will store its data and how it will point to the other elements and all these things. So any idea on how a linked list will be stored and how the data will be occupied in the memory of the system?
Using nodes which are reduced.
Sorry.
So we use nodes to
Oh,
store our
yeah.
linked. And
Yes. So we will use nodes, right? So basically, when coming to the linked list implementation, we have something called as node. Node is a combination of data and the reference point. So this is called as node, and this node will have two things. One is data, and the other one is reference point. So in a linked list, we'll have multiple elements which are arranged in sequence. Sequence in the sense we will have multiple nodes, and this is how the nodes will be. And each node, as I'm saying, will have a data along along with that we will have something called as reference point. So this is called as singly linked list. Let's talk about other kinds of linked list like double linked list, circular linked list later. So basically a node is a combination of data and the reference variable. So the moment we add something, it will be added into the memory location, but we the previous element in the list has to know where the next element is there. For that, we have something called as a reference point. So this stores, this node has two parts. One is data, and as I'm saying, and the other one is a reference point. In this reference variable, or in this reference location, we will store the reference of the next node. For example, I have the let me say the reference of this particular node is A, and the reference of this particular node is B, and if the reference of this particular node is C, so this A will be stored into this reference variable. So it says to the it says that the next element or the next node to this particular node is A. In the similar manner, B is the reference of this node and it will be stored here. So it says that the next element to this particular node is B. In the similar fashion, C will be stored into this particular location. And at last, if there are no elements that are being added to the list, we will store the next reference variable as null. So this is the null that we need to store here. So it is null. So the first or the starting node is called as root node. So this is the root node in the linked list. So these are the terminologies that you need to, this is head, or also a root node. When coming to linked list, we call this as head. So we call this as head. Head is the starting node of a linked list, and starting from the head, we will have the other elements, and other elements references will be stored in the previous element. So this is how the elements will be tagged in a linked list. So what are the advantages of linked list when compared to an array list?
Insertion and deletion will be like quick because of this reference.
Yes. So insertion and deletion is quicker when because of these references. For example, if I need to delete this particular node, I doesn't need to traverse all the other nodes which are to the right of this particular node. Instead, I can just tag the reference of the next node to the previous node. So that is why insertion or deletion in a linked list is bit faster. So if I want to insert some node here, I just has to store the, let's say I want to insert a new node here. So instead of moving all other elements to its right to the next places, I can simply release the reference here, release the reference of B in this particular node. Instead, I can add it here, and the reference of this can be stored here. It's as simple as that. So that's the reason when compared to array list, insertion or deletion is faster in a linked list. But the disadvantage is, along with this, we need some space for these pointers as well. Along with the data, we need to have some other data that needs to be allocated for storing the pointers. So let's say if my data is taking some X number of bytes, my along with that, my pointer will also take me some data which is Y. So this is not memory friendly, but it takes more memory when compared to array list. But insertion as deletion is bit faster, is very faster, and when compared to array list, we doesn't need to move or traverse the elements here and there when we are storing the elements into storing an element or deleting an element in a linked list. So this is called as head, and we call this as a data point, and we call this as next is something which stores the reference of the next element. So this is what a single linked list is. It is single linked list, and this is how the data will be stored, and it's sequenced in a single linked list. Now let's look at doubly linked list, or doubly linked list, whatever it is. So any idea on this, how the data will be stored in a doubly linked list?
Yes, Mohan. So the
Yes, sir,
double.
it is a
The reference pointer will
Yes.
point and back and forth. Again, it will be pointing to the reference point, the before one.
Right. So it's simple. The node itself is different. It now it will store the both the previous elements reference and the next elements reference. So that's why it's mentioned as doubly linked list. So it will have three branches. One is the reference to the previous node, and the next is the reference to the next node, and the data will also be there. So it will have data, and this stores the reference of the right nodes, and this will store the references of the left nodes. Right node reference and left node reference. I hope you have good idea on this doubly linked list as well, and the advantages of it. And any idea on the circular linked list?
Circular, like the tail is pointed again pointed to the head.
Yes, the tail will be pointed back to the head. I mean, the last node in the singly linked list, or I mean, in the list will be pointed to the first node. So that's the reason we call it a circularly linked list. Circular linked list. So, for example, this is my doubly linked list, and everything will be there. So the last elements, reference. What will be the value of this in a doubly linked list, and what will be the value of this? I mean, this is the head and this is the tail, and basically this will store the reference of this, and the reference of this, and the reference of this will be there in this, right? In a similar manner, the reference of this will be stored here, and the reference of this will be stored here. So it goes on. So in the last node, the value of this particular reference is null because there are no other elements to the right of it. In the similar manner, for the head, the reference variable of the previous element is null because there are no previous elements before this, right? That is doubly linked list. And circular, when coming to the circular linked list, the reference node of the last the tail element will be the reference of the first element. That's why we call this as circular. So so it is like circular. The last nodes will be pointed to the first node will be pointed to the second, third to the last, and last to the first. Whereas in the doubly linked list, it is not like this. Instead of storing the first reference variable, it is null because there are no right elements. So that's the that's the differences between singly linked list, doubly linked list, and circular linked list. This is an overview, and I hope you have good idea on these things. uh, right, can we move forward with the implementation of the single linked list? I hope you have a knowledge, and it's clear for all of you.
Yes, sir.
Yes. So let's move forward and understand the implementation of the linked list, and the same applies for double linked list and circular linked list as well. So let's take a notepad. So what do we need to construct first? We need to have a node, right? So inside a node, what do we have? We have data, and we have something called as next, which is the reference for the next node. So we need to create a node, and the process to create a node is I'm creating a class, and I'm calling it as node class. So this is my node, and my node should have two things. One is data. It can be any data structure. So let me take it as int. I need to have data, and also I need to have a reference to the next node in the linked list, right? So I need to, in a node, I need to store data and also the reference to the next element. So I am creating something called as node of type, and there is a variable called as next of type node, or reference type node, because we are storing the reference of the next node in the linked list flow. So these are the two things that we need to have in a node. And I also need to create a constructor to store the value into the data variable. So this is my node, and inside the constructor I'm assigning uh, this value to a to the data in the node module, and simply I'm just assigning null to the next variable. This is the single node that we have created. So node is something, as we are discussing, it will have two things. One is data. It will have two things. One is data and the other one is, so one is data and the other one is reference to the next node. Reference to the next node, right? So this is how our node is. So we created a class for this node, and inside the class we created two variables, and one is of type int, and one is of type int, and the other one is of type node because it stores the reference to the next node. So we instantiated the data variable inside the constructor of this node. You can see it here. So inside the constructor, we are initializing the data and we are storing null for the next reference variable. So here we are storing null and here we are initializing the data. So this is the class for the node. Right now we are done with the node class. On top of it, we will get linked list. Public class linked list. So by default, we will know the last element because last element's reference will be equal to null. So we doesn't need to have anything that points to the last element in a linked list, because if you see the sequence of elements in an array list, the last element, we can easily recognize the last element in the linked list because the reference variable of the last element will be null. It will not be equal to any value. So whenever we encounter the next as null for a particular node, we call that as the last node. But we need to have something that points to the start of the node. So if we have multiple nodes in a linked list, so let's say I have n number of nodes that have been stored in a linked list. Out of all these nodes, I don't know which is the head node, right? So that's the reason we need to have the reference of the head node that has to be stored. So there is no need to store the last element's reference. Why? Because the last element can be recognized uh, by 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 uh, by reading the value of the next or the reference node of a reference value of the node. If it is equal to null, we can say that as a null value, but it is not the case with the head cannot be recognized until unless we store the reference of it. So it is very important to store the reference of the the reference of the head node, so that we will know like this is the start point of the linked list. So that is the reason I has to create a reference variable inside the linked list for the head. So I have created a reference variable for the head here. So this is my linked list class. I have a node structure and I also should have a reference to the head node. So these are all will be sufficient for the linked list, and uh, uh, we doesn't really need to have any other things that needs to be stored in a linked list. We doesn't need to store the address of the tail because we can recognize it by using its next reference variable, which will be null. But we need to have the reference for the node. So this is one part. We created a node and we have seen what all data that needs to be have, or what all variables that needs to be have in a node. And when coming to the linked list, a linked list will have multiple nodes of this structure, and it also should have a reference variable for the head. Now in a linked list, we can insert, we can remove, or we can delete, and we can add the what all we can do. We can print the elements in an array in a sequential order, and we can delete the elements at different node points, right? So let's see each and everything in detail. So now let's see how do we implement the insertion operation in a linked list. So this is the linked list base structure. This is linked list base structure. And now let's see how to insert the elements into an linked list. So now we need to insert elements to linked list. So for that, I'm taking a method called as linked list insert is my method. So it needs to have two parameters. One is the linked list to which we want to add the new node. Insertion is nothing but adding a new node to the linked list, right? So I need to have two parameters for this. One is linked list comma, other one is data in data. So this data is something that I need to add, and list is something to which I need to add this data. So this is the method. The next method I do have inside this, my implementation should be something like this. So node new node is equal to new node. So I'm passing data for this. So what this actually means, what will happen with this? Node new node is equal to new node and data. I have done this. So it basically means we are creating a new instance for this node, right? So this is my node class, and we are creating an instance for that node class, and we passed data to that particular node class. It means we created a node, we created a simple node, and let me show you here. So what we have done, so we created a node. So if you see this, we call this node class, and this node class will have data and the next variable, and we are passing the data here. Whatever the data that we want to insert, we are passing here, so that this data will be stored in in this data variable, and next will be equal to null. So now we created a node with that particular call. By invoking or creating instance for the node class, we are creating a node, and we are also passing the data to that node, and the reference variable by default is null, right? So the reference variable is null, and the data is passed, and whatever data that we are passing will be stored inside that particular instance. So this is an instance that we have created for the node. So this is an instance that we created for the node. So now hope everyone is clear with this, right? uh, Creating an instance and storing the reference of that. So the next step is, to this new node, let's store the next value of this as dot next is the variable. This is the reference of this particular node that we have created, and it has a reference variable called as of type node, and which is next. So inside to this next, I'm storing as null. For now, we created a node which has data as the value that we are passing, and the reference to the next node is marked as null, because for now we are not tagging this to any other elements. Now here we will have three cases. The first case is if the linked list that we are passing is empty. So if this linked list is empty, so the new node that we are creating will be the head node, right? So that is case one. So case one is if the list is empty, the list is empty, node we are adding is will be the head node. will be the head node, right? So the case 2 is if there are some elements, in the list, we need to tag the reference of adding node to previous node, comma, next node reference to adding node, right? Hope you understand this. So understood this. Like we are trying to insert a variable, a new element here, and now we will have some linked lists in this way. So we have a linked list which is already present, and now we want to add a new uh, node to that particular linked list. So this is my linked list I do have. So earlier the reference of this will be stored here, the reference of this particular will be the next node will be stored here, the reference of this node will be stored here, and this is how the linked list will be. Now if I want to insert this particular list, this particular node at an index 2, what I has to do, it's as simple as that. So I need to store, instead of storing the reference of this into this, I need to remove this reference. So I has to remove the reference of the next node. Instead of this node, I need to move the reference of this into this. So now I need to tag the reference of this variable into this, and the reference of this into the adding node. So this is my second case, right? This is my second case. So the first case is if I have empty linked list, so the node that I'm adding will be the head node. Here in this case, this is the head node. If I have some elements in the linked list, so this is my process. I need to move, instead of tagging the next reference, I need to tag the reference of the newly added node to the previous node, and the next node reference has to be moved here. So this is the second case. Now let's quickly see the implementation of both these cases. So I need to put an if statement here, and I need to check if the head is null or not. This is my case 1, and in the case 1 I have something like, so the list that is passed is, this is the list dot head. So head is the reference that will store the reference of the head node, and for every linked list we have something called as head. So for this linked list we are accessing this head, and if this is equal to null, I mean, we can say the list is empty. Now what we need to do, we need to store the reference of the head. I mean, list dot head is equal to node that we are adding, that is new node. So this is the node that we want to add, and that will becomes the head, and this is the reference, control C, and this is stored into the head, because this says that our list is empty, so that whatever node that we are adding will be the head node. So now we are done with this. Now we need to move forward, and we need to implement the second case. If my linked list is not empty, so I need to move forward with my second case. So let me take node last is equal to list dot head. So I'll iterate in while loop here, because I need to fetch the last node, and at the last I need to add it. So this is a reference to the head node, control C, control V dot next is not is equal to null. So we need to change the reference to the next node. Last is equal to last dot next. So it's important to understand these lines. So what we have done, we are taking the reference of the head node and we are storing into a reference variable. Now this last will refer us to the head node and we are checking last dot next. So so this is what we do have here, and we are pointing the last to the head node now. Now we are checking whether last dot next is nothing but this is the value, right? So if this is not equal to null, what we are doing, we are assigning the reference, we are assigning last dot next to the last. So last dot next is something, the reference to this, the reference of this is moved to the last. So now my last reference is this one, because I moved last dot next to the last. Earlier my last reference variable is pointing to head. As we moved this reference to the last, now my last is pointing to this reference variable. And now I am checking again if last dot next is null or not. As this is not null, what I has to do, again the reference of this particular which is there in this next has to be moved to the last. If I move this reference to the last will be pointing to this particular node. In this sequence we are traversing to the through the list until unless we encounter node reference dot next as null. So here if you consider last dot next is should not be equal to null, but here in the case it is not true, because here the last value is null. So as it is not equal to null, we will move to the next statement. So these three lines helps us to traverse to the last node in the list. Okay, so this is the loop that helps us to traverse to the last of the list. And here we need to add something. That something is last dot next is equal to new node. So what we have done here, so we want to add this node and we have null here. Now we need to move the reference of this to here. So that's we have done. So this is my last. Now last dot next has null. I'm replacing that with the new node. New node is nothing but the reference of this particular node that we have created. If you see these lines, we have created a new node, and that is the new node is the reference of this particular node. So now we are storing this new node reference to the last node. So that is done. So it is null here. So the last node reference is null here. So this is how we can add an element at the end in an array list. So these three lines will help us traversing through the list, and the last line will help us store the reference of the last node or the newly added node to the last node. So with this we are done with adding the element at the end and the end. So we just need to return the list. Okay, so hope everyone understood this, right? How do we add elements at end, and if it and we need to check whether list is empty or not, and we need to add it at the start.
Yes, sir.
Yes.
Yeah, now we need to add in the middle, right? So when we are adding in the middle, what we need to do, we need to have some reference to the previous node as well as the next node, because the previous node's reference has to be changed with the current node, and the next node reference has to be stored here. That is how we need to add an element in the middle, right?
Yes.
Yes. So for that we need to have something like this. So do we need to have an index? So do we need another parameter called as index here?
Yes.
When we are adding element at particular index, we need to have the index, because so it tells us at what place we need to add the element in an index, right? So for that we need to have this, uh, we should have this index. Now what we need to do, we need to iterate through the loop, and we need to make sure so the first thing that we need to check is last dot next should not be equal to null, and along with this, what is the index? So let me take two variables here. One is int index check is equal to 0. I'm initializing with it 0. Int index is equal to index check is equal to index check is equal to the index that we are passing. So now inside this while loop, what we have to do, we need to have something called as previous as well, right? So we need to have some other reference variable for the previous element, node previous, because we need to also have a something called as previous that needs to be stored. So next inside this, I'm storing like this: previous is equal to uh, last dot next. And let me take a new variable called as current node. Control V is equal to control C and control V. So this should be my while loop, right? So now we are keeping index as 0, and inside this we need to increment it as well. Control C, control V is equal to control V plus 1. So int index is equal to 0. We are checking whether it is equal to the check index. Okay, so this is the while loop that we need to run. So initially we are initializing with this 0, and we are incrementing that whenever it is matching the index. We are just traversing through the list, and we are incrementing the index. When it is matching, what we are doing, we are capturing the previous as well as the next node. So now once we are out of this loop, we has to do this way, right? What needs to be done? So previous dot next. So in the previous, shift home. So inside previous dot next is equal to previous dot next is equal to what has to be stored here? Hello. Into the previous element, what I need to store?
A new node's reference.
Yes, it is new node, because it's simple here. So we are trying to add a new node, and the reference of this new node is new node. We created a new node with some data that we are passing, and the reference of this node is now this. Now we are at this index, and we have the previous, and we also have the next. So the previous is last is something which will stay here. Last dot next is something that points to this. So here it has, this is the last, right? Last dot next will have a reference to the next node. So last dot next reference is taking, we are taking into the current node. So this will be our current node, and this will be our previous node, because this is last and this is last dot next. So into the previous node, into the previous dot next, we need to store the reference of the new node. So the reference of the new node here is new node, right? New node is the reference of the new node that we are creating. That's the reason I am storing the reference into this. So the next is what I has to do. I has to store the reference of the next node into this node, right? So new node dot next, so new node dot next has to be current node dot next, current node dot next. So this is my new node. In my first step, I stored the reference of this node to the previous node, and now in the next step, I need to store the reference of my next node to the current node. So that's the reason I captured the next node and the previous node, and the next node, I mean current nodes next, current nodes next will be, or the reference will be stored inside this, into the current node. So this current node is just the reference of the next node, right? So that reference will be stored into the new node that is created. So now it is a continuous thing. So this node will have the reference of this node will have the reference of this, and this is a chain, continuous chain that we achieved using this, using the references of the nodes, and we manipulated the references here and there to add the element at a particular index. Hope everyone understood this, right?
Yes, sir.
Okay.
Yes.
So let me pick someone, and I'll ask them to repeat this again, because this is a base. With this, we can do the deletion at a particular index, insertion at a particular. I mean, we have seen the insertion and how printing the elements and all this depends on this, and this is very important. I'll ask someone to explain this. For now, let me pick Samir to explain this to everyone, so he can do it better, I feel. So, Samir, can you go forward and explain, revise this, what we have discussed till now? A brief overview, not in detail. Samir, are you there? Okay. Uh, Let me pick Hemali. Can you go forward?
Yes, sir, I can explain. Hello.
Yes.
Uh, can you hear my voice?
Yes,
I'm
we are
audible?
able to.
Okay, okay. So first, for like linked list, we have two things in that. Like one is a node, and other thing is a data. So we have to create a first a node class. In that, we have to give data and like the reference, which is a pointer, like a node next. In that node constructor, we have to like give the next is a null, and data is a value, whatever we are passing into the node. Then we have to create one insert method. In that we have to take two parameters, node and data. Then we have to check first condition. If the node is null, then we just give the data to the head, and after like inserting all the data, we check whether like after that we just check like if there is a no the head is not null, then we move forward and we add the data. If you want to insert data like in between, we have to create a two then we have to create a two pointer, the like the current node and the new node, to give the reference of the new node to a current node. Yeah, we have to give a reference to the current node. So in the new node's reference to the current node's next. So that's how it will recognize the both of the nodes. Yes, sir, that's it.
Yeah. So now
Is it?
we have seen the three cases: adding at the end, adding at a point, adding at an ending. Now, so now we are done with the insertion. Let me go with printing the values. Printing all the values in a stack, all the values in the linked list. Now let me run again. Dikshita, can you try implementing like the scenario here is we need to print all the values in the linked list. Can you tell me the piece of code that helps us printing all the values in the linked list? So we have already seen traversing through all the elements, right? Now I request you to tell me the piece of code that prints all the values in the linked list.
Sir, I traversed like in a different way.
Okay.
So I used it like a temporary variable to hold the reference. Like if you add or if you delete, if you add a node in between or wherever you add.
Mm-hmm.
And I just traverse through like, and I have checked like before the linked list is empty or not before all these.
Mm-hmm.
And I gave a temporary variable like TMP or something, anything like any
Okay.
variable you can take.
I'm writing the code. You can say me like what I need to assign for the temp. So for sure,
Okay,
it should
let
have
me.
parameter called as linked list. So others also please try to implement this on your own. Like just try to write the piece of code for printing all the values in the linked list. We have already seen traversing through the complete list, right? So to print the elements as well, we just need to traverse through all the linked list, and we just need to print the data, which is a variable in our node structure or node class, right? So that's all we have to do. So
Sir, for printing, we don't need that linked list, no, in that parameters. We just simply check like we start from the head. If the head is not null, then we traverse and we print. That is the
Sir, I
logic.
just gave the method in the chat for traverse.
okay. So, but Hemali, this is needed because what do you want to print? How this function knows where is your list and what list you want to print?
Sir, if we give like a node temp is equal to head, we start from the head node. So that will know, no,
Yeah. So,
if we give as a
what?
head.
So head is something that will refer to the first node, right? Or to the start node.
Yeah, yeah,
So,
yeah. To start node.
which list head will be you will take like? So you need to have the reference to the linked list, right? So if I have a reference to the list that is passed as an attribute. So if I don't have this list that is passed to this method, so let's say copy this and here I'm using the head of this dot
So in the
list.
main method, you have to create instance for that list,
Yes,
linked list,
yes, that list has to be passed to this method.
and you add the elements in that,
Yes.
or
So
add,
without
delete, whatever you want to do.
this reference, so maybe you can create a static linked list. I mean static reference in the main class, and you can use it across, or else you need to pass this. So these are the two ways. So if you don't want to pass this, you need to make it as a static in your uh, what to say in your main class. So it's like we need to take the reference of the head, and we need to create a while loop again. So inside the while loop, the same traversal carry forward, so it should not be equal to null. Control C, Control V. This should not be equal to null, so it is not last here, so it should be temp dot next should not be equal to null. If it is null, there is that indicates it's the end of the linked list that we do have. So I need to sys out here. What I need to sys out? Temp dot data, right? So temp dot data will print me the data in the node, and in the next node I need to move temp is equal to temp dot next. So this is how we will print the values. So we are pointing the temp to head, we are checking the next is null or not, and we are printing the value in this temp. Temp dot data will give the data inside that node, and then and the next we are assigning the next node reference variable to the temp. So we are moving to the next node, and again we are checking whether next is null or not. We are printing the data. So it keeps on going until we reach the last node, because the last node's reference or the next variable will be null. So this is how we'll print the values in a what to say in a linked list. Correct.
Yes.
Yes, sir.
So now let's move forward and try to delete an element in a linked list. So how do we do that? So let me quickly create an variable static linked list delete key, and I need to have two parameters inside this. One is as usual the linked list from which we want to delete the values, linked list comma int key, at what index we want to delete the key, right? So again the first case is if it is null, like if the list is empty, what we has to do?
Have to return.
Yes, we will say that key is not found because it's a null linked list, and the key that we have passed will not be there. So if it is not the case, if it is in the middle, again we need to delete that node, and the next node's reference has to be stored into the previous node. So now we have seen adding the new element. Now we need to delete this element. So if you want to delete this element, here we'll have the reference of this, right? So here now we inserted it, now we have the reference of this here. So this node's reference is stored here. Now we are deleting this element, so this has to reference to this next element. I mean this should be stored into this. The deleting node dot next has to be stored into the previous node. That's all, we doesn't need to do anything else, because that is what. So this is the reference to the next node. When we are deleting this, the next of this previous node has to be assigned with the next of the deleting node. That's the only thing that needs to be done, so that this node's next reference will be will be this node instead of this node. So this will be allowable for garbage collection, as it doesn't have any references that's been stored. Okay, so that is pretty much about the deletion, and for that we just need to develop the implementations. So let's look at the first case. So as usual, I need to take the reference of the head of the list. So I'm creating a reference variable current node is equal to I need to take the list dot head. So from here we will start. So the case one is, if it is found at the first place, let's say my current node should not be equal to null, it means that it should not be an empty linked list. So if it is an empty linked list, we will not find a value with the key that is given, right? So in an empty linked list, we cannot find that. So there is no case doing it, taking it forward. It's not equal to null. It should not be an empty null. And also current node dot data is equal to key. So we are checking the head node is equal to the key that we want to delete or not. So here I need to pass the data int key. So this is the value that we want to delete from the list. So we are checking it whether the linked list is empty list or not, and it should not be empty list. And if it is current node is the head node right now, and the data is equal to key, if the current node or the head node is equal to the if the head node is equal to the key that we want to delete, then the next steps that we need to do is we need to assign the list dot head. So the head has to be changed to the next node, right? Current node dot next. So now we are deleting the element at the starting place. So this matched our key. So now we need to delete this node. Basically this is the head node. When we are deleting the head node, what will be the head node? The next node will become the head node. That's the reason the head reference has to be changed to the next node. So that's what we are doing. So head is changed to the current node dot next. Current node dot next is nothing but this is our current node, which is the head node, and this is what we want to delete. And current node dot next will have the reference of the next node, and which will be the head node in our new in our case. So as we are deleting this, the head has to be changed to this node, and that we are doing it here. So current node dot next, this will have the reference of the next node, and that reference will be stored into the head node because this will be the starting node as we are deleting the head node. So with this we are done, and we can say something like I have deleted the node. Once it is done, the reference to the head node will not be there, and it will be allowed for garbage collection. As no references are there for the head, we can simply that will be simply cleared by the garbage collector. We doesn't need to do any operations to delete that. So we can print out like key is found and it's deleted, key found at head and is deleted. So now we are done, and we can return the linked list. So we can return the list now as we deleted the key. So this is the first case that we do have. If the element is found at the head, I mean at the head place, if it is found at the head, we just need to change the reference variable of the head, and it needs to be pointed to the next node. So now this is done, and the next case is if you want to do it at if the key is found at middle of the linked list. So what we need to do, we need to traverse through the list, and then we need to check we need to delete that node in the sense, as I told you, we just need to change the reference of this to the previous node, so that it will be pointed to the next node, and this will be allowed for and this is allowed for the garbage collection. So for the piece of code for that is, current node should not be equal to the null. Current node should not be equal to null, and current node dot key is not equal to key that we are passing, or in our case it is data, right? So the node will have has a parameter called as data. So now what we do have, we need to traverse to that key. is all what we have to do. So until unless this is matched, once we reach to the key that we want to delete, this will become false and it will come out of the while loop. Still then it will traverse through the linked list. So we need to take the previous element, because to the previous element we need to store the current element's reference, right? So I'm taking previous element and I'm assigning it as new node, and the next element, current node should be assigned to current node dot next. So we are taking the reference of the previous node and the current node, because these are the two things that we need. We doesn't need the next reference, because we are not reading any values from this. We are reading the next of the current node and the next of the previous node. We are just assigning the next of the current node to the next of the previous node. That's what we are doing. So we are bothered only about the previous element and the current element. So once it is matched, it will come out, and here is what we need to change the reference variables. So what we need to do, previous dot next should be assigned with current node dot next. So if you are done with this, we are moving the next reference node of the next element on the current node to the previous node, right? So this is moved to this now. So the next of the previous node is reassigned with the next of the current node which we are deleting. So once it is done, we can say it is deleted. We can say sys out key found and deleted, key found and deleted, right? So with this we are done with deleting the key as well at a middle position. And the last case is, if the list is null, if the linked list is null, what we need to do, if the current node itself is equal to null, what we need to say to the user, we need to say that key not found, and it's an empty linked list. We need to say that key not found, because as this is a null, this is an empty linked list, we will not find the key not found, as it's an empty linked list. So this is how we can delete a particular node from the linked list, and these are the three cases that we can see. So if we are seeing the node at the start of the linked list, we just need to point the head of the linked list to the new node, that to the next node. In the second case, if you are deleting the element in the middle of the linked list, and this is the process, we need to traverse to that node, and we just need to change the reference variable of the current node dot next has to be assigned to the previous dot next. And if the list itself is empty, we can say the list is empty and we cannot delete it. So these are the three cases uh, that we has to do, when that we need to implement when we are deleting a key. And we have seen insertion, deletion, which are the major properties or the major things that the linked list is more feasible for. And we have seen that, and we have also seen printing all the elements in an array list, and we also seen the basic structure of the linked list. So this is how this is the implementation of the linked list, and the double linked list will also be the same. So instead of single assigning, we will need to do multiple assigns in a double linked list. So here what we are doing, we are tracking only the next element and previous elements when we are inserting, when we are assigning or when we are inserting some element into an array. In the double linked list, we need to have the track of the previous element, next element for sure, because the next element reference will be stored and the previous element's reference will also be stored into the element that we are adding. So that this double linked list and circular linked list with implementations will be same. Additionally, we will add some references. We will need to store some other references, the previous elements references also in the doubly linked list. So you can find them over internet. So you can easily understood their implementations as well, I hope. So this is all about implementing a linked list in Java. So let me ask you, like can we call linked list arrays, stacks and queues as linear data structures, right? Because all the elements that we are adding are sequential, like one after the other. So that's the reason we call the linked lists, arrays, stacks and queues as linear data structures. And now we are gonna study about recursive data structures, which are like trees, graphs and all, which is another part of what to say in data structures. Before going to that, let me cross confirm with you everyone, like uh, everyone got this right, the implementation of the linked list, because this is the base. And if you are able to understand this, it's like a cakewalk for you. The double linked list and circular linked list will be like a cakewalk for you, and you can easily grab them. So before going forward, I'd like to take your confirmation, like whether you understand all these implementations of the linked list or not.
Yes, sir, we understood.
Yeah. So in the next session, someone of you can come forward with a demo implementing doubly linked list and circular linked list, and there won't be any much difference. It's just, as I told, it's just the references. As we have seen it theoretically, understanding the code won't be a big challenge for you, I believe. So with this, I'm winding off this linked list implementation, and I'm moving forward with another data structures called as trees. So we have a new data structure called as trees, and we call this as hierarchical data structures. Let's say we are into an organization, and we will have if you take the company's organization, on the top we'll have a CEO. Under him we will have different departments like financial officer, recruitment officer, chief recruitment officer. Okay. Under him, under the chief financial officer, we have again financial director. We have, so this is how an employees will be structured in an organization, right? So we'll have some managers, senior managers under him. So if you look at this carefully, so it is looking like a hierarchical data structures, right? Hierarchical data, right? So under the CEO we have a financial officer. Under financial officer we have a few other employees. Under the director we have managers and senior managers. Under a manager we can have multiple associates. So if you have ever used Teams or something, if you go to organizations tab, you'll see this architecture. So it will show us how the hierarchy of the organization is, and under whom you're assigned. All that stuff will be visible over there in the organization. So to store these kind of datas, so this looks something like hierarchical, right? So it's looking like a tree. Under one person there are many persons that are coming, and again it's repeating. So under CFO we have, under CEO we have CFO, under CFO we have again a new structure. So this is again a new, so this can be again considered as a subtree under the main tree. So this is the main tree. Under this is a subtree again. Here under this we have a subtree. Until unless we reach to a single element, This is looking like a recursive part, right? So hope you're able to hear me now. Hello.
Yes, sir.
Okay. So this is how until unless we reach an element of
Yes, sir, we can hear you. Just
so until unless we reach an element of length 1, it's an hierarchical structure. So this is a parent node. Under that we have a similar structure. Under CFO we'll have a similar structure. So this is looking, is this not looking like a tree? Like if you consider this, so it is expanding this way. It is starting with a single node and now it is expanding this way. So it keeps on growing and it has it's creating a multiple branches. So this is one of the reasons why it is called as tree data structure, and that's the reason we call this as hierarchical data structure. It's representing an hierarchy. If you take the other examples, if you take the folders in your file explorer, it's a hierarchical data structure. So inside the root folder you can have many folders, inside the subfolders you can have many folders. So it keeps on going until, so the last node, until unless you reach the last folder in your file system, it keeps on representing the same kind of data, hierarchical data. So that's the reason we call these kind of data structures as hierarchical data structures. So so let me represent these things in here. So this is, let's understand the terminologies that are associated with this tree data structure, and then we can move forward with the other things. So we have few terminologies that needs to be understood before moving forward with this tree data structure. So let me explain you all of them and then we will move forward. So tree data structure can be defined as a collection of entities called nodes linked together to simulate a hierarchy. So it's a collection of entities called nodes. So each part over here, so if you see this, this is one node, this is a node, this is a node. So each and every data that we do have is called as a node in this tree data structure. So this is the node, this is the node, this is the node. So everything that is over there is called as a node, and we call this as a link. So the one that is connecting two nodes is called as a link. So this is called as a link here. So this is called as a link. So this is the link traverse from the parent node to the child node, and this is the link. uh, this is the link. So each and every line that is connecting two nodes is called as a link. And one important point here is link is an is not a bidirectional ways, it's a unidirectional way. So we can move from the parent node to the child node, but we cannot move back from child node to the parent node. So this is very important to remember us. So we can move only from the parent node to the child node. Links are always unidirectional, it's not bidirectional. So this is also called as non-linear data structure. So this is not non-linear. If you consider linked list, arrays and all, they are all linear data structures because we are storing elements in a sequential order. But here it is not a linear. We call the trees as non-linear data structures or hierarchical data structures. So the topmost node in the tree is called as root. So this is called as root. The topmost node in a tree is called as root. And each node will have some data, as well as it will have some pointers associated with that to link the child nodes that are there with it. So basically the structure of each node in a tree will be something like this. So it's again like it should have a data. So it should have a data. Let's say each node in a tree should have a data, and also it should have the reference variables that points to the child nodes, right? So it has to tag itself to the child nodes. So to tag itself to the child nodes, it has to store the references of the child nodes. So that's the reason a node basically looks like this. It should have a data within it, and it also should have references for the next nodes. It can have any number of childrens. So those number of references has to be stored into this particular node structure. So for now we have two child elements. That's why I have for reference I have created two reference blocks, and these two reference blocks will store the references of the next nodes. So that is one important. So the topmost node in a tree is called as root, and the root's basic structure looks like this. It will have data, and it will have also blocks to store the references to the child nodes. So we are calling this as root, and we are calling these as childs of the root. Let me number all the, so it's easy for me if I number them. So let me number with a different color. So this is my one. Ama, ama. And this is my turn. So I numbered all the node. Now one is called as the root node because this is the topmost node that we have in the tree. 2 and 3 are called as child nodes of 1, right? Hope I'm audible to everyone. and you're listening to me.
Yes, sir.
Yeah. So this
Yes,
is
sir.
called as root node, and 2 and 3 are called as children of node 1. 2 and 3 are children of node 1. So just try to understand the terminologies. Now we know what is root, what is a children, and children of same parent are called siblings. Children of same parent are called siblings. Children of same parent are called siblings. So can I say 2 and 3 are the siblings of 1? Hello.
One is the parent.
One is parent,
Root.
2 and 3 are siblings.
2 and 3 are
Yeah.
sibling.
So 2 and 3 are the siblings of uh, parent 1, right? Is 5 and 6 are siblings of 2?
No,
5 and 6 are siblings
4
of
and
1?
5.
4 and 5 are siblings of parent 2.
Hmm. So the next point is any node in a tree that doesn't have a child is called as leaf node. Any node in a tree which doesn't have a child node or leaf node that don't have child. What are the leaf nodes here?
5.
7, 8, 5, 9, 10.
Yes, 7, 8, 5, 9, and 10 are the leaf nodes. Internal nodes. Nodes that have at least one child are called as internal nodes. So what are all the internal nodes in the above tree structure?
3.
Yes, we
4,
have
2,
1,
3,
2, 3.
6, 1.
Yes. So any node which have at least one children are called as internal nodes. So we know parent of parent is a grandparent. Parent of parent is grandparent. Child of child is grandchild. Child of child is grandchild. So 1 is grandparent of 4. 4 is grandchild of 1. So now let's understand what is ancestor and descendant. Ancestor, descendant. So if you are moving from the root node to the leaf node, I mean if you are traversing in this way 1, 2, 4 and 7. So first 7, 4, 2 and 1 are the ancestors, right? Am I correct? So in any tree traversal, if you're moving from 1 to 7, 4, 2 and 1 nodes 4, 2 and 1 are the ancestors, and for 4, 7 is the descendant. So the node which is coming below that is called as the descendant of that node, and the node which is coming on top of it is called as ancestor for that particular node. So these are the terminologies. One is leaf node. The important things here are we need to understand what is root node, what is link. We can also call link as an edge, and we need to understand what nodes are called as children nodes, what nodes are called as leaf nodes, internal nodes, grandparent, grandchild, ancestors and descendants, descendant and siblings. So these are all the terminologies that we basically use in a tree data structure. And we also know the links are not bidirectional. So this is the link that is connecting node 1 to the 3. It cannot be bidirectional. We can store only the 3's reference in 1, but we cannot move back from 3 to 1. So we call the links as unidirectional. So the other there are two other things, incoming edge and outgoing edge. If you consider the node 2, the link that is coming from node 1 to node 2 is called as incoming edge because it is coming to the node 2, and 4 and 5, these two edges are called as outgoing edges. So incoming edges and outgoing edges. Incoming edges or links, comma, outgoing edges. So these are all the terminologies that we do have with the tree data structure. And as I said, we can call the tree as non-linear data structure or hierarchical data structure, or we can also call it as recursive data structure because it's happening in a recursive way. And we have already seen this in merge sort, right? In the merge sort, how we are traversing, we are dividing the array into two parts, and we call this as a left child and we call this as a right child, and we are moving forward in a recursive manner because this structure, if we separate this structure from this structure, it looks like an separate tree structure, right? So for example, if I split this, so this is my left child. If I move this aside, it looks like a separate data structure, right? It's look like a separate tree. It has a parent node. It's a parent node which is called as root, and it has childs and it has subchilds, grandchilds. It has everything. So that's the reason it's like a recursive. If I remove this part, this looks like a tree. If I remove this part, this looks like a tree. That's why we call this also as a recursive data structure. So that's pretty much about the naming conventions that we use in a tree data structure. Now let me ask you a question. So if there are n nodes in a particular path, how many edges will be there? So let's say path in the sense, if I am considering, if I am talking about a path, you can consider any path. So this is one path. So this will be one path. So this is one path. And also this can be another path. So this is one path as I told you. So this is a path. This is also a path. This is a path. So number of edges that will be there when we are traversing the n number of nodes. Can we derive a formula for that? So let's say in a tree we are traversing through n nodes. Can we count the number of edges that will be we will encounter in that path?
It will be n minus 1 edges.
Perfect. So if we have n nodes, let's say here if you are traversing through this and we are traversed through n nodes, the number of edges will be equal to n minus 1 because we have 4 nodes, then the number of edges is 3. So if we traverse this path, if we move this way, so we have 4 nodes, the number of edges is 3. So if you are considering this way, we have 3 nodes but the number of edges is 2. So it is, if we have n nodes, the number of edges or the links will be equal to n minus 1. So this is one thing. And you can, even if you have a very bigger tree and if you know the number of nodes, you can simply say the number of edges that are associated with that particular path. And now there are two terms that you need to two other important terms, which is called as depth and the height of a tree or node. Depth and height of a node. So let's understand them. So depth and height of in a tree data structure. In tree data structure. So let's understand these two terms. So simply to keep it short, depth of a root node is 0. So then I'm saying the depth of a root node is 0. So then what will be the depth of this? Of 2 and 3 nodes?
1,
Right. So what will be the depth of 4, 5, 6?
2,
Yes. So the depth of 7, 8, 9 and 10 will be equal to 4. I mean 3. So this is all about the depth. Depth is nothing but length of the path from root to the node of the node to which we are calculating. If someone asks you to the depth of the node 3, it is equal to the length or length of the path from root to the that particular node. In that let's make it as dynamic, let's call it as x. So if you are talking about, if you are assigning x as 3, the path will be equal to is 1. So the path of that particular node is 1. So if you are taking it as 6, what is the path? So it is 2. If you are taking 9, it is 3. So it is, depth can be defined as length of path from root to x, or number of edges in path from root to x. So I'm writing here, keep it short. Depth is nothing but number of links or edges from root to the node we are calculating, to the node we want to calculate depth. Got it? So this will have a depth of 0, the root will have a depth of 0, and this particular structure will have depth of 1, and 4 and 4 5 6 will have depth of 2, 7 8 9 and 10 will have a depth of 10. Now let's understand what is height of a node in tree. Height of a node in tree is nothing but number of edges in longest path from x to the leaf. So let me write it again here. Height is nothing but number of links in the longest path from x. X is node we want to calculate height to a leaf node. So this is the definition for the height. Number of links in the longest path from node we want to calculate height to the leaf node. Let's say I have this node 3. I want to calculate the height of this node. So what will be the longest path to the leaf nodes? So let's say I have another leaf node that I'll add here. So let me add another leaf node here. So I have another node and I'm tagging that node to this particular. Let me add it here. So if I want to calculate the height of this node 3, what is the maximum or the longest path from this node 3 to the leaf node? So for the node 3, what are the leaf nodes? 9 and 10 are the leaf nodes, right? Am I correct? Hello.
Yes, Mohan.
Yes. So 9 and 10 are the leaf nodes. So the longest path is something like this. So
So
from
it will be
tree,
11, right?
yes, it
That's
will
the
be
last.
11. So this is the maximum path that we do have for the node 3. I mean the maximum path to the leaf node. So this is covering 2 links, whereas this path is covering 3 links. So this will be the maximum path, and we call that as the height. So number of links in the longest path to the leaf node is called as the height. So for node 3, the longest path is 3. So because we have 3 edges, 1 2 and 3, and this is the longest path. So if we consider the height of the root node, what will be the height of the root node? So what is the longest path to the leaf node? So the leaf nodes for the root is 5 7 8 9 and 11 are the root nodes. I mean the leaf nodes for the root node. So if we consider the longest path, so this is one of the longest paths, and the number of edges is 3, and this has 2, and this has 3, this has 3, but this has 4. This particular path has 4 links that are covered in the longest path. So the height of this particular root node is 4. So that is the difference between the height and the depth. Depth is something that number of edges from root to the node we want to calculate depth. So we are calculating from root to the node, and in the height we are calculating the longest distance, longest path to the leaf node. So we are taking the reference leaf nodes as the references, and from there we will calculate the height of the root, and the longest path will be called as the height of the root, height of the tree. Uh, Everyone got the difference between the depth and the height?
Yes, sir.
Yes.
Yes, sir.
So those, that's called as depth and the height of a tree. Now, based on the properties and based on how many children are tagged to the root node and how the children are tagged to the root node, we can classify the trees into different ways. So now we'll study about the classification of the trees. Tree data structure classifications. So the first one is binary tree. So a tree in which each node can have at most two children is called as a binary tree. So every parent should not have more than two children in the complete tree data structure. Such kind of trees are called as binary trees. Okay. So the condition for a binary tree is at most two children has to be there. At most two children is allowed. Two children are allowed. So hope you got an idea on what is called a binary tree and what is not. So let's say this is my data structure, tree data structure. Which tree is a binary tree here?
Tree
Tree A.
Yes. Tree A is the binary tree because to any parent in this particular tree, we don't have children more than two. But if you consider this case, here to this particular child node, you have again three nodes that are attached to this parent. So the condition for a binary tree is a tree, any node in the tree should not have more than two children. But here in this case, we do have more than two children. So for this particular node, we have three children. If you look at this, we have three children for this particular parent. That's why we don't consider this as a binary tree, because the basic condition is not achieved. Whereas if you consider this tree, every parent has at most two children. None of the parents have more than two children here in this particular tree. So this has two children, this has only one children, and this has two children, and these are all the leaf nodes. So we can call this tree as a binary tree. This particular tree B failed to achieve the basic condition of a binary tree. So a tree can be called as a binary tree if it satisfies, or if each and every parent in the tree data structure should not have more than two children attached or tagged to it. Okay, that is called as a binary tree. Now, hope everyone understood this binary tree, right? And now we can also classify this binary tree into multiple types. So the first one is strict binary tree. What is called as a strict binary tree? So the binary, we call a tree as a binary tree if each parent should not have more than two children tagged to it. So what is strict binary tree? A binary tree is called as a strict binary tree if each node can have either 2 or 0 children. I mean to say, so what is the condition for a strict binary tree? Each node can have either 2 or 0 children. Can we call this as a strict binary tree?
No, no.
Why? What's the reason?
Because the left side node has a one node.
Yes.
If it has a two node, it is like a strict binary.
Right. So the left side part of this particular tree has one children tagged to it. So, but for a strict binary tree, each node should have two children or 0 children, either 2 or 0. One is not allowed. So that's the reason we cannot call this as a strict binary tree. So if you remove this children or if you add another node to it, we can call it as a strict binary tree. So let's say if I add another node to this, I can call it as a strict binary tree. So now it becomes a strict binary tree. So the next classification in this binary tree is complete binary tree. So it's a little tricky to understand, but let's concentrate on this. So let me take a new slide. We have seen we know what is a binary tree, and we also know what is a strict binary tree. Now we are moving to complete binary tree. So the next classification is complete binary tree. What is called as complete binary tree means the definition that is given, that is provided for binary tree. Complete binary tree is all levels except last are completely filled and all nodes are as left as possible. So this is the definition of a complete binary tree, or this is the condition for a tree to be complete binary tree. All levels except last are completely filled and all nodes are as left as possible. So let me draw a diagram for that. So let me take a tree, something like this. So I have one node to the left of this. So I have three nodes to the left of this. So according to the definition, can we call this as complete binary tree? Before that, is this a binary tree?
No. No, sir.
So when this is not a binary tree, there is no point thinking about complete binary tree. So as one of the children of the root node has three children. So for example, if I take this as node 3 has three children. So this cannot be a binary tree. So once it is not a binary tree, it cannot be a complete binary tree. So first, before going to the classification, you need to understand, you need to judge whether this is a binary tree or not. Once you decided it as a binary tree, then only you need to go for the next classifications. So it failed to achieve the basic condition of a binary tree. So there is no point looking into the other classifications. So it will be a binary tree if I remove this. If I remove this. Okay. Now, is this a complete binary tree?
Yes, sir.
Is this a strict binary tree?
No.
Why?
The
Because it has
Oh yeah, yes sir, yes
one
sir. Because the left side node has no node. Yeah, it is strict binary tree.
It's a strict binary tree. It's also a binary tree. Is this a complete binary tree?
I guess it's not. Yes, sir. Yes, sir.
So let me explain you. Let me explain you this. So all levels except last. What do you mean by level in this tree data structure? So level is nothing but this is level. So all the nodes at the same depth can be called as nodes at the same level. So these two nodes are at the same level. So these four nodes will be at the same level. So the nodes at the same depth can be called as nodes at the same level. So that's a simple understanding of the levels. So we call this as level 0, we call this as level 1, we call this as level 2, and we call this as level 3. Now let's come back to the definition. So it is saying all levels except last level are completely filled. So in a binary tree, what do we mean by completely filled?
It has like two children.
Yes. So the
at
maximum
least two
possible number
children
of
at
children
last.
to any node is
Hmm.
2. So if a node is occupied or tagged with two children nodes, we call that as completed or completely filled in terms of binary tree. Because in binary tree, any parent can have maximum of two children. So that is the basic criteria that needs to be achieved to be a binary tree. So to be completely filled, every node should be should be occupied with two child nodes. So now coming back to the lines, all levels except last. So we need to exclude the elements or the nodes in the last level. Except the last level, all the nodes in the other levels has to be completely filled. Okay. So now let's check these two conditions. Is this node completely filled?
Yes.
Yes.
Is this?
Yes.
This is completely filled. This is completely
Yes.
filled. So this is this completely filled?
No.
No.
Is this?
Yes.
No.
Is this?
No.
No, right? Because
No.
yes. So we have some nodes which are not completely filled in another level other than the last level. So this is level -1, and here we do have some nodes which are not completely filled. So we cannot call this as complete binary tree. Okay. So it failed to achieve this case, except the last. We really don't bother about the last level. Last level can be anything, but but the other levels other than the last level has to be completely filled. Completely filled in the sense every node has to be occupied with two nodes. So that's the reason this is not, we cannot call this as a complete binary tree. Let me construct another tree for you, and let's discuss the other stuffs over there. So I have a tree this way now. Which every node other than the leaves, a full binary tree is a tree in which is got. So let me add it quickly. So there is a little change here that we need to understand. All levels except last. All levels except the last means, so this is the last level that we know, right? So this is the last level. But so if we consider this path, this is the last one, so we call this as the leaf node. So we need to exclude this. So this completely filled will not be applicable for this particular node which is coming at the end. So that's the little correction. So I interpreted in a wrong way. So this is the last node in this particular hierarchy, so it doesn't need to be completely filled. So if you take this path, this is the last one. If you take this path, this is the last one. So these are the last ones. So the leaf nodes doesn't needs to be completely occupied. So but the rest of the nodes has to be completely occupied. So that's the only thing. So if we consider that case, is this a complete binary tree?
Yes.
No, because so it satisfied this. All levels except the last are completely filled. That is true. All the levels except the last are completely filled, but all the nodes are should be as left as possible. I mean, all the nodes has to be as left as possible. If these two nodes are here, so these are not the leftmost nodes that are there in the tree. These are in the middle, right? So if I have nodes something like this, if I have nodes here which are tagged to this particular node, then we can call this as completely binary tree because all the nodes are as left as possible. So this is the most possible left that that a node can have. So it cannot be called as complete binary tree because of that condition. So these two nodes are uh, somewhere in the middlemost in the binary tree. So these two nodes, the last nodes, are not at the leftmost part of this binary tree. These are in the middle. So these are the two conditions. One is all the levels except the last are completely filled and all nodes are as left as possible. So these nodes are not leftmost, these are in the middle. So to achieve to be a completely binary tree, the nodes has to be on the leftmost possible. So the leftmost possible in this tree is this, to the nodes has to be attached to this particular parent. So as these are not attached to this, it's not a complete binary tree. So then what about this? Is this a complete binary tree?
Yes.
Yes, because it satisfied all the conditions. All levels except the last or except the leaf nodes has are completely filled, and all the nodes are as left as possible. We have the leftmost possible is completely occupied. So we don't have unfilled leftmost nodes. We can have any number of nodes to the right, but the leftmost should be occupied. All the nodes should be as left as possible. So the left that is possible here is that the children has to be tagged to this. As they're tagged to this, we can call this as completely binary tree. So this is completely binary tree and this is not a completely binary tree because the only reason is, so we don't have the leftmost nodes are completely filled, or all the nodes are not as left as possible. So that is the reason which is causing
I have
this.
one question.
Yes.
Sir, as left as possible means like if you have a one node, it has a right child and a left child. So if left child has also a right child and left child, then all the nodes should be like to the left. That is as left as possible, no? So or it's like from root you need to consider as left as possible.
Right. The level minus one, from level minus one we need to consider. So this is level minus 1. To this level minus 1, we are not considering the last one. All levels except the last, we are not considering. To the above level, so these are the above level ones. To in this level, the leftmost node is this node. So to this node, it should be filled. Without filling this node, if there are any nodes that are filled in the middle, we cannot consider that as complete binary tree.
Okay.
Got it? Level minus 1 has to be considered. So now let me ask you a question. So maximum number of nodes that are possible at a particular level in a binary tree, can we derive a formula for that? So we know the binary tree is something, for each parent we need to have two children, that the maximum two children that we can tag to a parent. So if we consider that maximum number of nodes at a particular level can be,
Level into 2.
sorry, what is that? So now our intention is to calculate the maximum number of nodes that we can have in a binary tree at a particular level. maximum number of nodes at a level in a binary tree. So I hope you're calculating it, so we can simply derive a formula for that. So maximum number of nodes at a level in a binary tree. Is this not 2 to the power of level?
Yeah, 2 raised to n.
2 to the power of level. So if you consider this is level 0, right? So we know what is level as well. So I call this as level 0. So this is level 0. These two comes under level 1. These two comes under level 4. And these two comes under level 3. So the maximum number of nodes at level 0 can be 1, 2 to the power of 0,
1.
which is equal to 1.
1.
And the maximum number of nodes that can be there at level 1 is
2.
2, because 2 to the power of 1. At level 2 it is 2 to the power of 2, which is 4. And
4
at
and
level
8.
3 the number of it's 2 to the power of 3, 8. So the maximum number of nodes, if we remove this node we can still call it as a binary tree, but the maximum is every node has to be attached with the two child nodes. That is the maximum nodes that are possible in a binary tree. So this is the maximum case. In the maximum case the number of nodes at each level can be 2 to the power of level. If someone asked you in a the maximum number of nodes that are possible in a binary tree at level 20, so if that is the question, instead of drawing the diagram and calculating the nodes, we can simply use this formula, like 2 to the power of 20 is the answer for that, calculating number of nodes at a particular level. Okay. So now
Yes, sir.
what is we have another tree called as perfect binary tree. Still now we have seen strict binary tree, we have seen complete binary tree, and there is something called as perfect binary tree. So what is called as perfect binary tree? So a perfect binary tree is if all the levels are completely filled, then such a binary tree is called as perfect binary tree. So if you see this, here all the levels except the leaf nodes are completely filled, right? So these kind of nodes is called as perfect binary tree. Perfect binary tree is the sense every node, every parent node has to be tagged with two child nodes except the leaf nodes. Okay, so if you consider this is a perfect binary tree because every node at every level is tagged with two children nodes. So this node is tagged with two children nodes, this is tagged with two children nodes. So these kind of trees are called as perfect binary trees. So the maximum number of nodes in a tree with height h. So let's say now we know number of nodes at a level level at a particular level, right? The formula is 2 to the power of level. So if someone asked you the number of nodes at number of nodes at a level 0, will say 1 because 2 to the power of 0 is 1. At level 2 number of nodes are 2 to the power of 1, which is 2. At level 2 it is 2 to the power of 2 4, 2 to the power of 3 8. Now if someone asked you to the maximum number of nodes in a tree with height h, let's say consider this case. So the total number of nodes in this tree are 8 plus 4 plus 2 plus 1, right? 7 plus 8, which is 15. 15 is the total number of nodes that are there in this perfect binary tree. Am I correct? So if the maximum number of nodes that can be there in a perfect binary tree is the question that is being asked, and for that we need to calculate for each and every level, and we need to sum up all of them. So I calculated for each and every level, and now I am doing a sum for all the values. 1 plus 2 plus 4 plus 8 will be equal to 15. So these are the maximum number of nodes in a perfect binary tree. Maximum number of nodes in a perfect binary tree. Now to calculate this in a generalized way, how do we calculate? It is equal to 2 to the power of 0. So 2 to the power of 0, how to keep it?
We can say 2 to the power of height minus 1.
2 to the power of, what is that?
Height of the node minus 1.
What is that? 2 to the power of, sorry, I'm not able to hear you. 2 to the power of,
Height, so if height is given, yeah,
okay,
we can calculate 2 to the
height minus 1 is what you're saying.
Yes, 2 to the power of height. Not height minus 1, sir. So 2 to the power of height and then minus 1.
2 to the power of height and then minus 1. Okay. 2 to the power of height minus 1. So what is the height of this tree?
That's 3.
So height is the maximum depth. I mean
Longest
the
path.
number of links
Yeah.
that we do have in the longest path, or we can also simply make it as longest depth from the root node to the leaf node. So, but this is the longest path, right? So the height of this tree is 3. So 2 to the power of 3 is 8. 8 minus 1 is 7, but it is not matching the right answer. So let's quickly derive it. It's simple. So let's say the next term will be 2 to the power of 1, because at level 1 next term will be equal to 2 to the power of 1, because at level 1 it is 2 to the power of level. So it will be equal to 1 plus 2 to the power of 2 at level 2 and 2 to the power of 3 at level 3. It goes on, right? 2 to the power of 3, and it goes on till 2 to the power of n. So let's say
So
we
in
have
that case,
n nodes, 2 to the power of n. Okay, if you sum all these terms, we will get the maximum number of nodes in a perfect tree. What we have done here, that's what we have done here. Now can you tell me the sum of this? It's just a mathematical calculation. Is this not a geometrical progression? This is GP, right? And the number of terms that are there in this GP is n plus 1. So as we are starting with 0, so the number of terms will be equal to n plus 1. From 1 to n we have n terms, and we have an additional term 0. So the number of terms will be equal to n plus 1. So number of terms are n plus 1. So sum of n terms in a GP is a into r to the power of n minus 1 by r. A into r to the power of n, r to the power of n minus 1 by r minus 1. So this is the formula for a geometrical progression. To sum of n terms of a geometrical progression is a into r to the power of n minus 1 by r minus 1. So if we calculate this using this, what is the first term? A is the first term and r is the common ratio. We all know that. So first term here is 2 to the power of 0, which is 1. So 1 multiplied by anything will be the same. So what is the r? R is the what we do call it as, so r is nothing but the next term by the previous term, 2 to the power of 1 by 2 to the power of 0, which will be equal to 2, right? Common difference we can get it from a2 by a1. So 2 to the power of 1 by 2 to the power of 0 will be 2. So we can take any two terms. So if we divide 2 to the power of 3 by 2 to the power of 2, the common ratio will be 2. So to any consecutive factors, the only change is the next factor will be a multiplication of 2 to the previous factor. So that is the common ratio, and the number of terms we do have here is number of terms that we do have here is n plus 1, number of levels plus 1 minus 1 by, so this is the whole numerator that we will get, and in the denominator, what is the r again? R is 2, 2 minus 1 is 1, so anything divided by 1 will be the same. So the formula to calculate the maximum number of nodes in a perfect binary tree is this one, 2 to the power of n plus 1 by n plus 1 minus 1. So what is the n number of levels that we do have here? It is
Height
4,
is there.
right? So this is 1 2 3 4, 4 levels we do have. So no, this is not, so this
We
should
can
be
say n is height.
n, or height plus 1.
Yes.
So this is equal to number of height plus 1. So if we have 4 elements, we'll calculate the height plus 1. So what is the height here? Height is 3, 3 plus 1 is 4, 2 to the power of 4 will be
16.
2 to the power of 4 will be 2 to 4, 4 8 16, right?
16.
So 2 to the power of 4 will be 16, 16 minus 1 will be 15. So the formula to calculate the maximum number of nodes at any maximum number of nodes in a binary tree is 2 to the power of height plus 1 minus 1 is the formula. So 2 to the power of, in this case, it is 3 plus 1 4, 2 to the power of 4 is 16, 16 minus 1 is 15. So we have 15 nodes in this particular tree. Got it? Is everyone clear with this?
Yes.
Okay.
Yes,
Now we can twist the same question. If the height is given, can we calculate the number of nodes in a tree? I mean, if the number of nodes are given, can we calculate the height? Now we are given the height. Now we will be able to calculate the number of nodes. So this is equal to number of nodes, right? Maximum number of nodes in a binary, in a complete, or nodes in a complete binary tree, or sorry, nodes in a perfect binary tree is equal to, in a perfect binary tree is equal to 2 to the power of height plus 1, 2 to the power of height plus 1 minus 1. So now we, height is given and we can calculate the number of nodes. If the number of nodes is given, can we calculate the height? This is given and we are asked to calculate this. Okay, now if you are given with this, can we calculate the height? Hello. So let's call this as n is equal to 2 to the power of 2 to the power of, let's call the h height as h plus 1 minus 1. So this is the formula to calculate the number of nodes, total number of nodes in a perfect binary tree. Now we are given height. If the height is given, we are able to calculate the number of nodes in a perfect binary tree. If the number of nodes are given, can't we calculate the height? It's just a mathematical calculation, right? So if you are moving minus 1 to the right side, to the left side, this will become n plus 1. So this is gonna become n plus 1 is equal to, n plus 1 is equal to, I am moving minus 1 on the right side to the left side. So this is gonna become 2 to the power of h plus 1, h plus 1. So 2 to the power of h plus 1, if 2 to the power of, if this 2 goes that side, it will be like log of n plus 1 to the base 2. So this will be equal to h plus 1. So anything to the power, anything base to the power, if you are moving it to the right side, it will become log to the base of that. So here the base will be 2. So here we will get the base as 2, because on the right side we have 2 to the power of, as we are moving that power to the right side, to the left side, it will become log to the base 2 n plus 1. So the leftover part is we need to move the minus 1 to the right side. So final formula of h will be is equal to log to the base 2 of n plus 1, log to the base 2 of n plus 1 and minus 1 will gives us the height of the complete binary tree. It's just a mathematical calculation. This is something that is very important to remember, and this is a derivation of that particular tree. So this is all about trees and the most important trees. We have seen binary tree. We understood the what is a binary tree. We understood what is strict binary tree, what is complete binary tree, and what is uh, uh, perfect binary tree. And we also have many binary trees, like as we have just seen. We also have balanced binary tree. We also have full binary trees, so you can go through them. And but most important things are this, and rest are all similar to them, similar to these what we have discussed. So you can also understand what is balanced binary tree. You can just search it and you can understand it. So that's pretty much about trees and linked list implementation. And now you can understand on your own the implementations of double linked list and circular linked list. And in the next session we will discuss about the implementation of trees, and then we will move on to graphs. So that's all for today. And if you have any queries, you can stay on the line, or else you can drop off for the day. And thanks everyone for joining.